Hi everyone, welcome to episode 7 of the Signal and Noise Large Language Model course. Today we're going to be looking at the assembly line, orchestration, authority, and failure modes. Why single prompt systems fail at scale. Single prompts and single agents may work in demos, but they often quietly fail in production. This is why many AI projects do not achieve their potential. In this section, we will address this issue. Capability is impressive, but reliability is deployable. Part 1. Decomposition dangers. We do not need to build a single omniscient agent to do all our work in one shot. Decomposition is breaking large tasks into several smaller ones, breaking those tasks down into even smaller ones, and mapping the hierarchy of the tasks. We need to understand the dependencies of each task, and we need to build a system that can handle high levels of complexity with grace. After all, one person can't be the CEO, facilities manager, and cleaner at once. The same is true for AI. Decomposition is risk control, not necessarily optimization. We decompose workflow to control failure, not improve intelligence. Decomposed systems have clear inputs and clear outputs. They have clear responsibility, and they're localized. The errors are localized, detectable, and recoverable. They have specific but limited tool access. We need to break our work apart until the failure becomes boring. An agent with 2 instructions and 1 tool is very unlikely to call the wrong tool for the instruction. The risk is not just a bad answer. The risk is infinite loops, it's hallucinated tools, and it's data destruction. Avoid the trap of over-engineering. Do not split trivial tasks into dozens of agents. Each step has one decision. A human can express its purpose in 1 sentence, and we also need to consider latency. Don't decompose if the handshake is longer than the thought. It's not about complexity for the sake of complexity. We want appropriate and proportional complexity, minimum necessary complexity to get the job done safely. Context pollution occurs when unrelated instructions compete for the model's attention. Context pollution is the silent killer. Your model isn't crashing, but it's getting less effective, less efficient. Models weigh all instructions simultaneously, which can lead to priority confusion, median answer collapse, inconsistent reasoning paths, and getting lost in the middle. Clarity dies in crowded rooms. So why not just be very explicit in the prompt? Explicit is not the same as isolated. Isolation requires separate execution contexts. We must design failsafe into our system. 1 task per agent, 1 goal per execution context. Here, execution context is a fresh API call with no knowledge of the previous ones. When you talk to the large language model itself, you talk to it once per goal. Context windows are not just storage. They are processing buffers. Filling them up with irrelevant tokens slows down the process and makes the model dumber. Clear segregation of contexts makes the model more efficient. Do not confuse or overload your agents. But specialization does have a cost. More agents means more transitions and more handoffs. The transitions and handoffs can induce latency, they can create deadlock, and they can potentially hide responsibility. We should always assume that agents are liabilities until proven otherwise. Functionality is the asset we're looking for. Agents sprawl without ownership. Sprawling agentic systems lead to context degradation and information loss. Every agent must have an owner, a reason to exist, a strict timeout, and a fallback. Handoff isn't just slow, it's lossy, and lossy systems lead to bad outcomes. The solution is not to deploy agents sequentially, but to route them dynamically. The router, an agent in itself, is lightweight. Its job is only to classify and select, no tools. The solver, for any given task, is specific and deep. It executes the task in clean context and has specific tools and instructions. We need to separate the decision of who does the work from the work itself. Resist the trap of giving the router the power to do simple tasks. This still leads to lossy systems. Even the high input must go to the greeter agent. Once you add greeter tasks to the router, it is easy to keep adding more tasks. Soon you're back to God mode agent again. To reinforce, separate the decision of who does the work from the work itself. Part 2. Orchestration misuse. Sequential chains are easy to build and easy to break. A chain assumes perfect upstream output, which can be rare, although we can design our systems to improve this, and deterministic downstream logic, which is impossible. The failures are silent. The model corrects the grammar of the hallucination, making the lie more difficult to catch. LLMs don't crash, they just produce garbage outputs. And one weak step poisons it. Everything after suffers. Pipelines fail at their weakest link. The trap is to blindly trust upstream outputs. Validate all outputs between steps and treat every handoff as an untrusted output. Structured JSON or similar outputs are easier to validate. If step 1 produces an invalid output, then the system should reject it. Here schematically we see input, which is correct, leads to error, which leads to garbage, which leads to failure, which leads to the wrong output. Pipelines fail at their weakest link. The consequence of misclassification is confident hallucination. If you ask the poet agent to do maths, it won't refuse, but it will write a poem about maths. Specialized agents don't always know that they can't answer. The solution is conservative routing. Conservative routing is confidence threshold and semantic distance checks. If the agent isn't 90% sure, it should pass to human review. The danger isn't that the work will go to the wrong place, but that the agent will try to answer it anyway. Routers are power concentrators. They decide what the system is allowed to do. Router mistakes propagate through the system. A small error at the start can be a massive error at the end. A butterfly effect. A misclassification is not a small error, which should not be considered a small error. Misclassification sends the work down the wrong path. It exposes tools that should not be used for that problem. A router is not just a classifier, it defines the system's intent. A chain fails because a step breaks. A router fails because it misunderstood the intent. The former is a crash, the latter is a security risk. Parallel processing can increase robustness, but only if the errors are not correlated. Parallel agents can make correlated mistakes and reinforce shared bias. An aggregation can mask uncertainty. Majority voting does not fix hallucinations. We must confront the model monoculture. 3 models may give the same incorrect answer 3 times. If 10 people walk into a room and 9 of them agree that there's a dragon there still isn't a dragon in the room. The one person who disagreed is still right, because dragons don't exist. Confidence amongst clones is just reinforced bias. So how do we solve it? We need to force disagreement. Force a competition of ideas. Include variance or confidence scoring. Increase the model temperature to force diverse outputs, and use heterogeneous parallelism. You can also use role prompting, optimist versus critic, to reveal different areas of the map of the model you are using. If you let 3 students copy each other, they will get the same answer, but it doesn't mean it's the correct one. Part 3. Human in the loop. Human in the loop is not supervision. Watching the AI work does not make the system safer. Human in the loop does not imply authority, it injects it. By default, the AI should have 0 authority. The humans are not the spectators, they are a state interrupt. The human must give the LLM permission to continue. Humans must be more than passive observers. Human in the loop is a breakpoint. Execution stops immediately. Human in the loop is a key. Humans provide the cryptographic signature. And humans in the loop is active consent. Silence is not approval. Dashboards with no control give the illusion of authority. Human in the loop converts synchronous pressure into asynchronous safety. It decouples the speed of the AI from the speed of the safety check. All external side effects require a gate and go signal. Authority must be injected, not implied. Human in the loop must also have default fail-safe conditions. If the human goes for lunch, should the system continue? Here are a couple of solutions to this problem. Default deny. If the process is not approved, then it fails after a defined time interval. Granularity. Don't approve a whole chat, improve a single tool call. Supervision is a passenger in a self-driving car. You can scream, but you can't stop. Human in the loop is the brake pedal. Human in the loop does have issues. It's a cognitive burden, and the gatekeepers do get tired. If you stop everything for a human, the human will stop caring, and the human will defer to fluent outputs. This leads to reduced attention from the human, increased automation bias, humans assuming that the logic is as flawless as the output, and the rubber stamping effect. Selective, risk-based sampling is better than total intervention. Idealistic safety becomes pragmatic safety, because humans fatigue before the system does. Risk-based sampling is programmatic filtering. User interface should highlight confidence intervals and raw data. If you want your human to catch the 1% of dangerous errors, you can't make them review 99% of the cases. You need to filter the signal from the noise. Only engage human in the loop if the confidence is low or the stakes are high. For example, ask for approval for refunds over $100 or ask for approval if the semantic distance is greater than 0.4. After 20 decisions, the human brain defaults to yes to preserve energy. We must design our system with that in mind and to avoid it. True accountability requires the power to change outcomes. We value things more if we help build them. So steering the output forces engagement and cognitive ownership. Read-only approval encourages role abdication, and binary approval is a trap. A yes button is too easy to click when distracted, because if you can't change it, you don't own it. And we need to enforce or encourage ownership within the organization that we are building within. From the human's point of view, if you force a user to edit, you break the system 1 thinking and force system 2 thinking. System 1 being fast and automatic, and system 2 being slow and deliberate. Product managers hate this because it slows down the workflow or hurts conversion. But we are designing for safety, not speed. Friction sometimes is not a problem. It is a requirement. Clicking approve is like scribbling your initials on a terms of service. No one reads it. Steering is like writing a check. You do check the number before you sign it. Humans in the loop need to become co-authors because steering breaks the trance of scroll and nod behavior. The passive observer becomes the active editor. Again, friction is not a problem, it is a requirement. Part 4. Anchoring the system. State, memory, and failure recovery. State prevents narrative drift. It replaces what the model remembers with what the system knows. No hidden assumptions, no implicit memory, and everything is inspectable. If it's not written down, then it's fiction. The distinction between model memory and system state is the difference between stable and unstable AI systems. The model memory may be fuzzy, probabilistic, and drift-prone, but the state memory is structured, deterministic, and inspectable. It flows from step to step throughout the system. If it's not written down, then it's fiction. Narrative drift is when the AI slowly forgets the original constraints as the conversation gets longer. As a user or as a designer, don't assume that the model will figure it out. The models prioritize newer tokens over older ones. States extract the key variables from the history and inject them as high priority instructions. So 4,000 tokens of chat may become 50 tokens of JSON. And it's the best JSON, it's the best tokens, it's the highest protein information that the system needs to execute flawlessly. Do not let the agent imply missing context. States allow for unit testing. The context window may change, but states lock them in. You can't debug a paragraph, but you can inspect a variable. Ensure that you have explicit null values and explicit uncertainty flags. Beware of implicit context. For example, if a letting agent received an email from a client saying that they had moved, the model would assume that they'd moved house. This is implicit context. They could have moved on their position whether or not to buy. They could move their appointment. State should remain address null until confirmed. The state anchors truth, but persistence anchors progress. A demo will run until you close the laptop. A product will survive a server shutdown. Without persistence, long workflows fail and context is lost. Persistence enables audits, retries, and rollbacks. Production systems must survive delays, crashes, and most importantly, humans. The question then becomes, doesn't this slow the system down? Yes, of course, but it also makes the system safe. It prevents silent failure. Rollbacks mean that your system does not have to start from zero every single time there's a problem. And this also allows us to use AI asynchronously, because speed without safety is reckless. Better answers require asynchrony. Stop trying to squeeze everything into a single request. This causes model collapse and bad outputs. You need to stop building chatbots and start building job runners. Synchronous agents are vulnerable to network issues, but asynchronous agents can be left to think in peace. For example, fail-safes, webhooks, let the system notify that it is finished, and status polling, let the user interface check in on the system from time to time. You shouldn't let a browser timeout kill an expensive system task. Most AI failures are organizational, not technical. Failure typically occurs because one of the following: unclear ownership, authority leaks, institutional complacency, metric fixation, and overtrust. AI amplifies structure, whether that structure is good or bad. Any production AI should answer yes to all of these simple questions. Can it pause? Can it explain what happened? Can a human override it? And can it fail gracefully and safely? If you can't stop it, you can't trust it. If it can't explain itself, you can't trust it. And if it doesn't know when to stop safely, you can't trust it. Reliable AI is not intelligent. It's restrained structure and authority. It's decomposed to local failure. It's rooted to preserve intent. It pauses when the risk is high or confidence is low, and it persists to enable accountability. Quiet systems, well-engineered systems beat clever models every day.